Stuttgart is located in Germany. The citizen has a pride of the Mercedes-Benz. Today, we are talking about museums design and construction. Let's go on a first one of the final presentation.
Stuttgart was used as a quarry in the past. Over time, it has become the center of the automobile industry. Mercedes-Benz is headquartered here, and the Benz Museum attracts numerous visitors every year. As Benz grew up, it needed a new museum. The new museum had to meet the larger space and required exhibition route. UN Studio proposed a design that meets these two requirements. Architect Ben van Berkel was inspired by the double helix structure of DNA. The double helix structure has continuous characteristics, and this structure was applied to the building to show the continuity of the exhibition movement. Visitors take the elevator to the top floor. Here, visitors can choose between two routes to go down. The exhibits are organized chronologically from old to new. However, there were many construction difficulties in the process of building the Benz Museum. The first is the ground problem. The second is the implementation of double helix. And the third is the freeform design. The museum site was a quarry where mineral waste such as limestone was piled up. And during World War II, the remaining bomb had to be tested. Due to the previous two factors, the original shallow foundation plan had to be abandoned. Therefore, they used plank pile method, which are in-situ concrete driven piles with retrievable casing tubes.
First, set driving pipe in place, fill in stopper concrete and ram in. Ramming in the driving pipe with 3/4 pile hammer, and the tubes are fitted with waterproof seal at the foot. After forming mushroom-shaped base at this point cylindrical, the necessary volume of footing concrete is driven in. Therefore, the expanded pile foot provides sufficient friction force for a short length. Next, reinforcement cage is installed and provides the structure with stiffness. After concrete is added, the casting tube is recovered.
As we use plank pile method, we can reduce the impact of the problem mentioned earlier and withstand sufficient load with relatively short pile. One pile created like this come together to support the Mercedes-Benz Museum about 850 piles. A slab is placed on these piles to transfer the load to the pile. The slab has 3 cores, and the 3 cores has a larger load. Therefore, slab under the core is thicker than anywhere else with a larger load. Find out more about the core. The 3 main cores are located in the center of the building. The Benz Museum transfers load through the main core to the foundation. The following architecture elements are created sequentially and are connected to the core to transfer the load. The load of ceiling is transferred to the mist lamp, and then the load of ceiling and mist lamp is transferred to twist. Finally, the load on the structure is transferred down through the facade support. To mist lamp, we had to consider 2 main points in the structure of the mist lamp. That is, the weight reduction of the mist lamp on the load and the insertion of ventilation system. Therefore, we solved this with use of hollow gutters. It is not only an excess element, but also an important load-bearing factor and serves as a curved beam. It needs an element to support the load of mist lamp and ceiling. It is twist.
Twist is a major load-bearing structure that supports exhibition levels of more than 30 meters without intermediate columns. The top surface of its twist becomes a circulating lamp that connects smoothly between exhibition spaces. If you look inside, the twist consists of a box girder with individual crosswords. There are some problems with the twist. First problem is that the linkage to a core is not sufficient. So, a satellite core as additional supports are also required. 2 bulkheads between the core and the satellite bears not only the weight of a twist, but also a mist and a collection floor. In addition, the twist structure is connected as one, which in itself provides enormous weight. Therefore, we create a twist structure in the form of a hollow box during the construction process, and also stands loose to bearings connected to the facade supports. Therefore, all supports consist of different adjustment angles and lengths. While in level 0 to 2, the column axis is inclined uniaxially outwards, The column axis from levels 3 to 8 tilt inwards on two axes. So that a load transfer from two standard story supports to a special story support was required on level 2. Therefore, using twist structures, the Benz Museum has a unique structure to create an exhibition space without columns. After this structural analysis, the most important topic is the complex construction process of freeform building. Then, how to construct this freeform building in detail. Typical construction process methods can be limited in many cases. There are three main cases. The first is the construction process of steel rebar. Twist was the most difficult task in designing Mercedes-Benz Museum steel frames. There are two problems with this. First is the problem of long and bending rebar transportation. Second, it is difficult to design rebar after first load analysis. How did they solve these two problems? If you look inside the twist, rebars are laid out. Due to its size and complexity, twist steel frames are pre-bent at the factory. And then, it was cut into transportable pieces and delivered to the construction site. The dimensions of this particular twist needed great precision in terms of design and construction. Developed over time with more and more occult structure models, the twist geometry was improved up to the final layout. In its final design, the twist was created as a three-layer steel composite structure. The three-dimensional load-bearing behavior is shown below. The steel structure 1 consists of a truss of steel hollow sections, which transfers the load to the inner edge of the twist. The main load path runs along the steel structure 2. After analyzing the compressive stress flow through strut and tie models, high compressive forces were found along the inner edge of the twist. The load is transferred from the inner edge of the twist to the steel structure 3 located within the slab. After, the H-beam is welded to steel structure 3. The H-beam is extended to connect with the core, which eventually transfers the load from the twist to the core.
Next, the second is the construction process of formwork. There was a problem with the use of formwork. Commonly used two types of formwork have difficulty implementing twist or mislength with high curvature. The solution was to implement double curve unit form via 3D customizing. Using 3D customizing formwork, uniform method was suitable for implementing this. This method assembles geometrical form of three-dimensional wood frame into uniform, and use 3D customized formwork because they are irregular. Timber can easily be made into any shape or size. Therefore, they use the triaxial CNC milling machine to create delicate shape. This 3D customized formwork is created by overlapping multiple panels. Finishing with wood panel, it becomes element of uniform method. The 3D customized formwork unit is itself transferred to the site and assembled in the uniform method. These moves units constitute the entire formwork. How did they position many formwork units? During the technical design phase, the method was used to specify the location of the formwork using VIM and number it to connect it. In this Mercedes-Benz Museum construction site, it can be seen that customized uniforms are positioned delicately, and we could identify the number for each surface. When numbering each form unit, it requires prior analysis that both cutting and coupling scale on double curved surface must be considered. In fact, the curvature was analyzed for each double curved surface, indicating that the unit's number was recorded in unit surface. And formwork was numbered and categorized according to curvature analysis. In conclusion, the wood support is produced to match the curvature analyzed by the CNC milling machine cutting, which brings them together to uniform. However, due to the double curved surface of the unit, they couldn't exactly implement panel. Therefore, the final surface is completed by bending the wood panel by manpower. Next, to reduce the possible layout error at the construction site, connect and fixate the units between them as shown in this following video. And after installation of other component, they carry out concrete pump according to shape of the curved form. However, due to the use of freeform, it is difficult to carry out concrete compaction process with external force. Final problem is construction process of concrete compaction. When excluding the concrete compacting process, the compressive strength is very poor because air bubbles are created inside the concrete burst. The second is the incorrect combination of aggregate and cement, which result in a large deviation compressive strength in concrete. However, Most of the concrete structure in the Benz Museum are freeform structure. Therefore, the dimensions of the structures need to be more precise. These structures are difficult to compact concrete. Therefore, they require the use of self-compressed concrete, pumped from the bottom to the top instead of poured down from above as the usual method. The use of SCC improves constructability and workability, and don't have the compacting work directly on each structure by self-compressing to fit the tree structure. This is our final presentation. Thank you.